What is a dimension? Now, this term dimension actually has different meanings, has multiple definitions. And specifically here, what we're referring to is the meaning of the word in the context of units and measurement. But the other definitions of dimension are closely related to the units and measurement definition. So in this video, we're gonna take a look at all of the different ways the word is used to clear up any confusion. Okay, but first, let me go ahead and give you the exact meaning of the word dimension as far as units and measurement. All right, so once again, as we talked about in the previous video, you're a caveman, cavewoman, observing the physical world around you, trying to characterize these different phenomena around you, and thinking about how could I potentially describe the extent or degree of these phenomena. So like measure the phenomena, and then you start listing out different phenomena, and you would start with what's most obvious. So for example, the spacing between points or objects. Okay, and you call that length and give it a variable L. Okay, there's also something that's obvious is there's like a duration aspect of the world. There's things that happen before, that happen in the present and after, in the future, and you call this time and give it a variable T. And then there's also what you notice is things are being pulled towards the ground. And what you're noticing is, in that case, is weight. As a caveman or cavewoman, you're noticing weight. But at present, we have a more advanced understanding of this. And so I'll put that as mass, which is technically not weight. And I'll give that the letter M. Okay, but then you also notice that there's other phenomena, like the speed of a leopard, let's say, how fast it's like moving across space, that's not really its own fundamental quantity. It's kind of a function of what you're calling the fundamental quantities. It's you name this velocity, but you realize, well, that's really a combination of it's like how it's moving across space in a certain duration. It's a function of two fundamental, what you're calling fundamental quantities, and I'm saying what you're calling fundamental quantities because even the fundamental quantities are a definition, a human definition. It's just these are what's, from our perspective as humans, what are most obvious. You know, there's nothing more fundamental as far as we're concerned than length. There's nothing more obvious than length, spacing between objects. But I just want to point out that it could have been the case that velocity seemed most obvious to us. That seemed the most natural, and maybe it is. You know, you think about Newton's first law. You know, an object in motion tends to stay in motion. Things in space just go with constant velocity forever, and unless they're interfered with. So you could have switched length with velocity, and then in that case you would say that length is derived and a derived quantity, and you would have said that length is velocity times time, and instead of length here you'd put velocity. So, but these are the most obvious, and so we call these fundamental quantities. And what's interesting is that these three here are technically, from what we understand today, that every other quantity that you could think about measuring, every other quantity, no matter what it is, related to temperature, light, electricity, sound, anything, every other quantity is a derived quantity with respect to these three fundamental quantities. So, like temperature, for example, you might say, well, temperature is its own unique quantity. No, temperature, we know the essence of temperature is it's an energy. It's the average kinetic energy of molecules, and energy is a force times a distance. Force is mass times acceleration. So m times length per time squared, and then times a distance, length. So energy is mass length squared per time squared. And it's the same idea with like electrical voltage that's like a potential energy. Light intensity, that's energy. And that's why there's certain unit systems, and we'll talk more specifics about unit systems in a later video, but there's certain unit systems that they use these three fundamental quantities, like the CGS system, the centimeter gram second. That's the three fundamental quantities, and that's the way the system is defined. However, the main system that is the primary system that we use today in science and engineering is the metric system, or the SI system. And again, we'll get into more specifics of what exactly the metric system is later. And they've decided to go ahead and assign more fundamental, even though that these are technically the only three true fundamental quantities, as far as we understand it today, they go ahead and assign additional fundamental quantities. For example, so I'll put a line here to distinguish these. They also say that temperature is a fundamental quantity. And in the previous video, I didn't assign any variable to temperature because I really wanted to distinguish that these are the only true fundamental quantities. But now I'll go ahead and give it a variable. Theta. Okay, so we're thinking through the perspective of the metric system, the SI system now. Again, that's the most popular system in science and engineering, and it's trying to be universally adopted. Okay, so we'll give it the variable theta. And we talked about, so why are we assigning this as a fundamental quantity if it's technically not one? Because it's still, at least from our perspective, it's still in its own kind of realm or in its own dimension. If you use another meaning of the word dimension, it's in its own dimension, right? But I didn't just use the word dimension from the units and measurement definition, but that's another meaning of the way we use the word that I'll talk about later. So yeah, it's in its own realm. We still think about temperature as you have that from our perspective. If you were a caveman or cavewoman, and it's still the case today, length is its own kind of area, time is its own kind of area, mass is its own kind of area, and really temperature is its own kind of area as well. That's its own world. So as far as the SI system, we go ahead and leave temperature as a fundamental quantity. Okay, we also, electrical stuff is its own world, right? So electric current, we say, is a fundamental quantity, and we give that variable A. All right, light coming from the sun, electromagnetic radiation, that's its own fundamental world, it seems, its own realm. So we say luminous intensity, and we give that variable J. Again, even though like electric current and luminous intensity are like these are all you could look at as energies. Okay, now to me, I would think, why not do something related to sound as well? But they don't do that. This is it. These six. Now, I'm going to draw another line, and there's actually technically there's a seventh fundamental quantity, and this is related to the amount of substance. And in the previous video, I said mole, but I shouldn't have said that. Mole is a unit, and we are not talking about units at the moment. We're talking about quantities and dimensions, and I haven't told you yet exactly what dimension means. We're getting to that in a second. I shouldn't have said mole in the previous video. That's a unit, and units and dimensions are two different things. Units, dimensions, and quantities are all different. But if anything, dimension and quantity are more closely related than units. So I shouldn't have said mole. I should have said amount of substance. And we'll give that variable N. And this is definitely in its own category. There's three separate categories here of these fundamental quantities. Now, amount of substance, you might say, well, isn't that mass? No, here what we're talking about is we're referring to a count. A count. And that can get a little confusing because what exactly is a count? A count is actually it's not a dimension. A count is not a property of nature. It's not a phenomena. It's like an assignment we put to something just to help us organize what we're talking about, to keep track of things. You know, if you have two leopards, and you're thinking about mass, well, then you can say the count is 2, but really the underlying mass is 2 times the mass of a leopard. But the count is just a way for us to organize our thoughts and to describe things. It's not a property of anything. You don't measure counts. Okay, so now, but what is a dimension though? In units and measurement, the context of units and measurement, what is a dimension? All right, well, I'm going to go ahead and give you officially what it means now. But then we'll after that we'll go ahead and talk about the different ways the word dimension is used and how it could be confusing. Okay, so any quantity about the physical world that you can think about measuring, not just a fundamental quantity, any quantity, length, time, velocity, acceleration, energy, entropy, whatever. Any quantity you can ask or say, like, okay, that quantity, what is that quantity's dimension? What is the dimensions of that quantity? You can use the word any way like that. You're talking about velocity. Okay, well, what is the dimensions of velocity? What is its dimension? Okay, and so all that you're referring to there, when you ask what is the dimension of something, is you're going to, if you asked what is the dimension of velocity, you're referring to this. That's the dimensions of velocity. That's velocity's dimension. Energy. What are the dimensions of energy? Mass, length squared per time squared. That's what you're referring to. What are the dimensions of length? Well, in that case, it's just length. If the dimensions of a quantity are the quantity itself, then you know it's a fundamental quantity. Okay, but what about entropy? Entropy. We know entropy is, what are the dimensions of entropy? Entropy is energy per temperature. So in that case, you would have mass, length squared, per time squared, temperature. But again, these three are technically not truly fundamental, but it's in the context of SI, you would write the dimensions of entropy this way. Okay, but now what about amount of substance, N? Do we ever include that in a dimension of a quantity? Since it's technically not a dimension, or the more technical way you would say that is that it's dimensionless, which is kind of confusing in its own right. The difference between dimensionless, like angles, are dimensionless. So right now we're going to put counts, amount of substance, off to the side. I'm going to address what dimensionless means, why angles and amount of substance are considered dimensionless, and how do we use capital N in the dimensions of a quantity. I'm going to talk about all that in a separate video. Okay. Now, but before we get into the different ways the term dimension is used and how that all interrelates to the definition of dimension that we just talked about, it's first important to understand the difference between unit, what a unit is and what a dimension is, because these are definitely two different ideas, and so it's important to be clear on the difference. So a unit can correspond to any quantity, fundamental or derived, and it's just a reference that we use. It's like a tool that we use to help us with the measurement of that quantity, to conceptualize the measurement. For that quantity, we define units. It's these, in the term unit, the underlying meaning is one, like a unit vector, one. We assign a value of one within that quantity, velocity or length or whatever, energy. We assign a value of one and then use that as a reference. So for example, the leopard. You observe the leopard running, and after you see the leopard, you also see a cheetah, and you think to yourself, well, in terms of leopards, how fast is the cheetah? Well, the cheetah is like 2.5 leopards. So you assign a value of 1 to the leopard, and then you think about, well, relative to the leopard, how fast is the cheetah? Well, the cheetah is, if you combined 2.5 leopards, then you'd get the speed of a cheetah. Okay, but then you might say, what about a tortoise? How fast is a tortoise relative to in leopards? Oh, well, you cut the leopard by 100. You cut down the speed of a leopard by 100, that's a tortoise. So 100th of a leopard is a tortoise. But then that's not the most intuitive, because they're kind of in their own categories. One's really slow, one's really fast. So you make up another unit that you want to use for slower animals. You think, you say, okay, I'm going to assign a value of 1 to the snail, and I'm going to measure slower animals, compare slower animals relative to the snail. So in terms of snails, how fast is the tortoise? Well, the tortoise is a little bit faster than snails. It's probably 3.5 snails. So 3.5 times the speed of one snail, that's the speed of a tortoise. Okay? So do you see the difference? A dimension, you're referring to physical phenomena, that realm, the length dimension, that realm, that kind of physical realm where a unit is just this tool you use for measurement purposes, as an aid in measurement or an aid in quantifying or describing the degree, the level, the extent of something. Okay, but now, what about the other ways that we use the word dimension in everyday life, and how is that related, intermixed here? Okay, well, let's look at some of the different definitions of dimension. So I've got the Webster's 2025 dictionary, and there's actually only one listing for the term dimension. They've got two definitions in here, but a lot of times with words there'll be multiple definitions. So there's only one listing for dimension. And actually, when I searched the definition of dimension on Google, got a lot more of a comprehensive breakdown. So I guess Google is truly the king of information. So I got a lot more of what I was looking for through Google. Okay, but in the Webster's dictionary, so the first definition is the physical property of length, breadth, or thickness, also a measure of this. So here that they're talking about the dimensions of an object. You have a drawing with dimensions on it, with a 3D drawing, there's different dimensions. You can also look at this from this perspective of, three-dimensional space. In terms of three-dimensional space, well, what is the fourth dimension? That's head scratcher, right? Okay, now, number 2 here, the extent, scope, or proportions. Yeah, that's more of an abstract, and they're talking about in more of the abstract sense of like the dimensions of a piece of land in terms of how big it is, the extent of it. They're using that more abstractly. All right, now on Google, so let's see, a measurable extent of some kind. So, okay, that's the dimensions. The dimensions of the pond were 14 by 8 feet. And then kind of a sub of that is a mode of linear extension in 3D space. So like three-dimensional, right? Now here in physics, this is the one that's more associated with units and measurement, an expression for a derived physical quantity in terms of fundamental quantities such as mass, length, or time, raised to the appropriate power. Acceleration, for example, having the dimension of length by time to the -2. So yeah, there you go. There's the definition, the technical definition of dimension in units and measurement. Let's see, we've got an aspect or feature of a situation, problem, or thing. Sun-dried tomatoes add a new dimension to this sauce. Yeah, so that's kind of, there's another dimension to this. We say that sometimes, right? If you want to go down that path, you're going into another dimension. So why do we say that? And how is that related to what we're talking about here in units and measurement? Verb, so dimensioning, you could like dimension a drawing. Seats and backrest are dimensioned to withstand high loads. Mark a diagram with measurements. You dimension the diagram. Okay. So now I've refreshed your memory on the different ways we use this term dimension. And what I found is that this could be a little bit confusing when you, in terms of exactly how you use this term in the context of dimensions and measurements in science. And with all the research I've done, the official standard way of using these terms is kind of ambiguous. There's really no official way of how you're supposed to, other than, you refer to this as the dimensions of a quantity here, but outside of that, it's kind of subjective. So I'm going to give you the way that I like to look at it, that I find most intuitive. Okay, so I look at the fundamental quantities. But this amount of substance is not included in this, just something that, a phenomena of the physical world. I look at the fundamental quantities as those are dimensions. Now, whether or not I view it to where these are the only 3 dimensions, or these 6 are the only, I wouldn't refer to a derived quantity as a dimension. Velocity is not a dimension. Energy is not a dimension. It has dimensions. The velocity is its dimensions are length per time. You could ask, what is the dimension of velocity? But I wouldn't refer to velocity as a dimension. I would always refer to length, time, and mass as a dimension. Those are dimensions. And do I include temperature, electric current, and luminous intensity? It depends on the conversation or the thought process I'm having. It depends. if I'm thinking about the meaning of the universe, the fabric of the universe, then I'll go down the path of, okay, these are the only three dimensions. If I'm thinking about more of a scientific design, trying to reason through something scientifically, then it is easier to think about, well, look, temperature is its own dimension. So is electricity. So it just depends. Okay. So, but what do I mean that these are, why do I refer to these as dimensions? And, for that matter, like length, what does three-dimensional mean? Does length have three dimensions, like subdimensions? Well, okay, this can get really confusing. And if you wanted to, I'm not going to claim to be some advanced physicist or mathematician. The technical meaning of the word dimension and coordinate systems, I mean, you could go down into advanced math, and those guys have a way better understanding of what exactly a dimension is. And so I'm not going to go, we're not going that deep. But what I'm going to give you is what I think is a really good, helpful definition, just as a general engineer, or, you're not going into this extremely advanced analysis. Mathematical analysis, you're talking about string theory has like 10 dimensions apparently. And so we're not going down that path, but I've got a really good way of thinking about it that I think you'll find very helpful. Okay. So of the fundamental dimensions, and let's focus on these three as the fundamental dimensions and the meaning. I'm thinking about this as like the meaning of the universe. Okay. Length is very unique in the sense that it truly does, from our perspective, it really requires, to describe the position of something in space around us, it requires three separate numbers. You call those coordinates. Why that's the case, I don't know. It's really kind of trippy to think about. But like in comparison, time is not like that at all. Maybe in actual reality, from, aliens or whatever, or God understands that time actually is just like length. But if you think about it, it really is. Time you can't, there's no sub dimensions of like length. You can separate into three separate kind of coordinates to describe length. Time is just one. And same with mass. It's like the book, I think it was Flatland or Flat World, where the entire world everyone was living in 2D, two dimensions. It was a world of shapes. And this idea of the third dimension was trippy to people. And so you can kind of think of it that way. It's like maybe there is a fourth dimension but that's, in that context, I'm referring to spatial dimensions. There's spatial dimensions, there's temporal dimensions. Okay. But now you could go down this rabbit hole and thinking about what is the meaning of dimension and the technical meaning. Again, like string theory has 10 dimensions, but to make it easy on you, if you're not going into that level of advanced math study or physics study, think about it this way. Here is 3D space. X, Y, Z. And just to point out, you might say, well, couldn't you use a different coordinate system than like the Cartesian coordinate system? Yes, you can use any coordinate system, but no matter what you do, you're going to need three separate coordinates. No matter what if you use the radial coordinate system or cylindrical, you're going to need three separate coordinates, no matter what. There's no other way around it. It's really weird. Okay? But if you've got a point in space out here, so this is, let's say you've got, there's a point in space. Okay, from the meaning of life as we understand it right now, let's say we want to describe this point as much as we can possibly describe it. Okay, it's not just a point, there's an object here. So it's not just a point. Well, okay, to fully describe it, we would put parameters like we have to put its X, Y, and Z coordinates. We have to put three separate kind of what you call coordinates there. I'm calling that coordinates. It's X, Y, and Z position. Then you also put its mass. That's another kind of coordinate you can think about. If you look at all of these as coordinates, you put the time it is with respect to the universe or whatever. You put the time. You could put the temperature. However, temperature is It's not fundamental, so I guess you wouldn't put it. But you could put its temperature. You could put something related to electricity. You could put something related to the luminosity. It's any unique descriptor of something, its own fundamental descriptor of something. That's like it's a dimension. If we found a new dimension, the fourth dimension, that would be a new kind of coordinate we could put on this, a fourth coordinate. If we went down a wormhole or something and we found it into a new dimension, what's going to happen? There's going to be some sort of new measurable quantity. It's like if we went down a wormhole and now we're on parallel universes. Now we've got another coordinate of time. You have like the coordinate of time in our universe on Earth, but you also might be like in quantum mechanics. You can be in two places at once, apparently, something like that. Well, now we've got another dimension of time. It's another coordinate. You see? But you can also see that depending on the context, if you're talking about the meaning of the universe, I guess you don't include temperature, but you might include temperature though. You could describe this object's position, its temperature, its electrical, some sort of descriptor of its electrical property, I guess electric current, but you could look at it there's different dimensions to describe it. But its velocity, it's not its own dimension because it's a combination of the fundamental dimensions. But if we ever, if there was a new fundamental dimension that comes up, then that's a new dimension. You add that to the list here. You see? So now with that, then I want to point out that I wouldn't refer to, and I don't think this is actually technically correct either, you don't refer to like velocity as a dimension or energy as a dimension. Those aren't dimensions. You're not in the velocity dimension. Only the fundamentals are you call dimensions. Velocity is like it's two dimensions interacting together. Velocity is a function of the length dimension and the time dimension. But velocity itself is not its own realm. You see? But velocity does have dimension. Does have dimensions.